He's going to be giving this seminar today. A little background information, which I asked him to send me, so I made sure to emphasize the right things and not screw anything up. So Niels is a master's in civil engineering from the Technical University of Denmark, where he did a thesis entitled Shape and Dimensions of Ripples. His PhD is in coastal morphodynamics, also from Technical University of Denmark, and he did his PhD under Joran Fretso. Full hydromorphodynamics description of breaker bar development, and he continued that into his postdoc. And he's currently working at Deltares in the Netherlands, working with hydraulic problems related to coastal and offshore structures. And then what he's going to be talking about today is CFD modeling with OpenFoam.
Thank you. Thank you for having me here. This is the presentation I'll be giving. It's sort of a flyover of how we apply detailed numerical modeling for fluid flow and morphodynamics with the software package OpenFoam. And it will also include a section on how we deal with coastal structures, specifically rubble mound breakwaters. So what's the outline of the presentation? First, I'll briefly touch upon what is OpenFoam as such. Then, how are we modeling waves? We can do that just looking specifically at the boundary layer itself, or also include elements such as a free surface, wave breaking, wave-induced setup, and the entire package, essentially. Then I'll look at a couple of branches where we have been working with OpenFoam, and that will be sediment transport and morphology as a single branch. Then we have a different branch that is coastal structures and offshore structures, both breakwaters but also monopile foundations for wind turbines. And recently we merged these two branches, so now we're looking at sediment transport and scour erosion inside of filter layers, and those are some sort of converging these two branches into one, and then I'll end with an outlook. But first of all, who are we? I'm here from Deltares. We are an independent Dutch research institute for applied research. We do everything that's related to water, subsurface, and infrastructure. This also includes something like ecology, water quality, hydrological modeling, and classical hydraulic engineering topics. We have two main offices in the Netherlands and small branch offices around the globe, and we have more than 800 employees, a big part being PhDs and Master of Science. And we are mostly affiliated with numerical modeling, expert judgment, and also large-scale physical experiments. And the line you can see over here is our most recent toy. That is a 300-meter-long wave flume that can generate waves up to around 4.2 meters as H max, and is 10 meters deep, so it can create some quite spectacular views. And it allows us to test a large fraction of the dikes in the Netherlands at prototype scale. And that's the main reason that we have a facility like that, is that the Netherlands is prone to flooding. Well, we try to make it not being flood, but we want to be able to test our safety at prototype scale if possible. So, first, what is OpenFoam? Or as I have here in the title, open source CFD modeling. And that's within the last 10-15 years, OpenFoam has gained quite a lot of interest, especially with universities and afterward at consultancies, simply because you can download the source code and work from there. And it's being used and validated quite heavily. So what's the background? It's a multi-purpose CFD toolbox. Essentially everything that can, I'll take it first. It started Imperial College in the 90s, group within chemical engineering, as far as I know, needed a software package to study chemical processes in fluid. And they realized that everything within fluid flow is typically described by the same thing. There's something that changes in time. There's something that's being affected. There might be a gradient of the pressure field, for instance. There's some diffusion and some source terms. So if you don't assign specific properties to this phi, essentially you just have generic toolbox for describing fluid motion. Could be turbulence properties, suspended sediment transport, advection diffusion of different species, or whatever you now want to be studying. So essentially you have a package that allows you to build your specific tools for what you study. So where has it been used? So far I've seen examples, combustion engines with the moving parts actually igniting the fluid and expanding again so the cylinder goes up and down. There's chemical reactions in thermodynamics. There's plasma flow in the ITER. That's a big fusion reactor being built in France these days. And then there's classical problems such as flow or airfoils. The wind industry has been using it, and so also a lot of universities looking at renewable energies. And then where I come in, we use it for coastal and maritime engineering. And just a bit of visual. I've taken these pictures off from the internet. We have an example of an airfoil. There's a centrifugal pump here sucking water, sediment through, and there's actually temperatures. So there might be some combustion going on in there, not quite sure. There's propeller flows, probably used in ship design, and then finally free surface flows, where we'll be focused mostly for the remainder of this presentation. So why is CFD relevant for coastal engineering and research within coastal sciences as such? First of all, it allows us to test prototype designs without actually have to build a prototype model of it. So it allows us to go through a design process at a cheaper cost and potentially also at a faster rate. Furthermore, many properties in fluid flow are just very hard to obtain. How do we measure pressure in the middle of a fluid without putting a pressure transducer in there that then affects the fluid, and what are we then actually measuring? So we can extract properties of the fluid flow in a non-intrusive manner and thereby better understand the fluid motion and what's going on. And then this is also related to design process. What actually happens when we're going to design an engineering structure? What are the loading? How can we tweak a design to optimize or rather minimize the loading on a structure so we can save construction steel, for instance, in the final stages. And to have a bit of visual examples about what we've been doing, here is an example from a former colleague of mine. He looked at oblique wave impact on a crest wall on a breakwater. He was looking after trying to understand what wave is actually creating the largest forces on the structure and how large are these forces. And then that leads to the question, how much concrete do we have to put into the crest wall so it's not sliding off when a couple of waves hit the structure. Here, there's another example, gravity-based foundations and slamming waves. It's a big concern for the wind industry. Slamming waves as this creates very sharp impulse forces, can create vibration of the tower and create fatigue damage of the tower. But also, the slamming will create run-up on the pile itself. So normally you have to install an inspection platform somewhere above the sea level, but if you put it too low, the run-up will simply tear it apart And we've seen that in Denmark, where they had to reinstall the inspection platforms because they were simply gone after a couple of winters. And then finally, some of my earlier work here is morphodynamics of breaker bar systems under continued loading, and I'll come back to that graph later on. So modeling waves with OpenFoam. This will be a very brief overview of what we're doing. But essentially, we're looking at two approaches to model waves. And I've included oscillatory boundary layers because often if you look at ripple dynamics, scour around a pipeline, or things like that, the free surface somewhere up there doesn't really matter. We just want to look at shear stresses, pressure, sediment transport close to the boundary layer. So there we are just moving the water back and forth, and there's actually no free surface. And the other one is free surface flows, where I have an example of it here. The shaded area you see is a filter, so it's sort of this handball size cobbles that the waves are then interacting with and dissipating in this, and that's being used simply as a cover on coastal structures. And we're modeling that with a toolbox that is called Waves to Foam. That is the starting point for wave modeling in OpenFoam back in 2012. And you can see it gives a quite realistic image about what is happening in the flow. And what does it do? It can create linear, nonlinear waves. And we also couple it with external solvers that create nonlinear incident irregular waves, which is otherwise a bit problem. I'm not going into the theory on that, but there's essentially no nonlinear irregular wave solutions theoretically, so we need other means of describing boundary conditions. What we are looking at is that once the waves break here, part of the energy will reflect back into the open ocean. But if you're not catching this reflected wave component, it will just bounce off the boundary condition I have in my numerical model somewhere and then come back to the structure. And I would actually not know what wave field I'm studying. So the boundary condition takes care of absorbing the reflected wave energy, so we know that the wave field we're looking at is actually the condition that we want to study. And there's a small website here where you can see more about it. There are also alternatives to Waves to Foam, and that is IHA Cantabria has made some efforts, but I will not be going into that in more detail today. So, what to use waves for? Why are we even interested in waves? So, we are modeling waves, and so far I've seen branching out into sediment transport, morphology, and scour problems. We have coastal and offshore structures looking at the wave loads on structures, trying to optimize designs, trying to optimize dimensions of these things. And then there's also people working with maritime engineering, optimizing ship drag in waves, floating structures, could be renewable energy devices, and the like. And then recently we have coupled these two first branches into a coupled network. Just a small note that I'm here for Deltares today, and that's also where maintenance takes place today. But it all started back with my professor in 2007, Jørgen Fredsø from the Technical University of Denmark, so he should definitely also have part of the credit for where we are today with this type of modeling. But I will only focus on the first two branches, and maritime engineering is not really my field, so I'll leave it for someone else to talk about. So, sediment transport and morphology. What is needed for sediment transport and morphology? What we need to know something about the bedload transport, so the sediment running just close to the seabed. We also need to know something about suspended transport. It will be brought up into suspension, float away around for a period of time, and then it might settle on the seabed, or it'll just stay in suspension, but in any case leading to erosion and deposition patterns. And we're putting that into what's called as the Exner equation, where we're looking at the rate of change of the bed level equals the divergence of the transport field. And how to understand this? It means that if you have an area here on the seabed and more sediment is being brought into the area than leaves it, there has to be a rise in the bed level. It's the only way we can have continuity of sand, because where should it go else? And just a small PR for the paper Liu 2014. He's been doing some recent advances in how to make modeling of suspended transport easier. It's not easy today, so making advances in improving our capabilities. I'll not go into the details, but I'm happy with it. So, what have been done? From Technical University of Denmark, 2 recent papers where they're looking at scour and backfilling around marine pipelines. And this is taken from their paper in 2016. We have dots of the measured profile of a sandbed. So essentially what happened in the experiments, you put a pipeline on the bed and you start with a current in the flume, and you start getting piping underneath and erosion start taking place, and then the scour hole evolves until it reaches a certain equilibrium. And there are 2 cases. It's called clear water scour and light bed scour, where clear water scour is essentially only transport close around the pipeline, and light bed scour is transport of sand takes place everywhere because the loading is so large that it moves all over the place. At least conclusion is that we're quite far. We describe this process quite accurately with this comparison against measurements. So that was job well done for that. Then we have morphological development of ripples. This is some very preliminary but also old results, but ripples does deserve more attention in understanding, both from a laboratory field measurement campaign, but also with numerical modeling, where you can really start looking at small details and what affects the development. And while I keep talking, I'll put on a small video of an example. What we have here, oscillatory flow. You can see the coloring is a vorticity, so blue when the flow is in one direction and red when it's in the other direction. The bed becomes unstable. Small bed forms start forming, running back and forth, and you can see how the model actually allows these bed forms to merge. They become bigger, they become steeper. Elements sort of sand sliding on the steeper part will be activated here, and at some point they'll become so steep that you can see vortex shedding, which is these elements shooting off the crest of the ripples. So we can start studying these type of phenomena and then also start looking into effects such as irregular waves or nonlinear waves. To what degree do they change the direction of the sediment transport, and what is the net sediment transport over ripple beds? Just let it run through. Yes. But yes, this is quite in its early phases, so I hope to see more of this type of research in the future. But if we want to say coastal morphodynamics, we also need to say breaking waves. breaking waves are quite difficult to describe in the process. So we did a validation exercise against laboratory data by Scott et al. From somewhere in the US, I can't remember where they were. And we have here a fixed breaker bar profile. So waves in the laboratory will have been generated here at minus 4 meter or 4 meter water depth. And then they will come up, start shoaling at the top of the breaker bar, and then they will be breaking. And because of the trough, they're not really dissipating anymore on the lee side of the trough or of the breaker bar. And because we have wave breaking, we will also have a wave-induced setup. And both the breaking pattern and the wave-induced setup is largely quite well captured. Unfortunately, they didn't report the undertow profile, so we were not able to validate that those quantities. But quite happy with the result. And this is a snapshot of how the model looks like. This is essentially where the wave will be. You can see it allows for overturning waves. It predicts you the pressure field and the velocity components underneath breaking waves. So it's a way of really start studying and in a detailed fashion trying to get an even better understanding of how the system works and then essentially parameterize it and put it into the engineering models at the end of the day. Once we have a breaker bar or a breaking wave that actually works, we can also start adding sediment transport and morphodynamics. And that is something I did in my PhD. And I think one of the most surprising things from that was that quasi-steady breaker bars is not achieved because the loading in some way becomes smaller. Quasi-steady breaker bars actually achieved when the water depth on top is so shallow that the sediment can simply not deposit there anymore. If it tries to deposit, it's being moved away. So by increasing the wave loading, you reach the maximum allowed height of a breaker bar. So what you can see here is that on a time stack, it's basically just growing more or less in a fixed position. And when it reaches that position, it starts moving and migrating offshore, at least under these conditions.